Yeah, so in this final video of problem sheet 1, we're going to look at question 3, the last question, in which I'm asking you to solve a simple finite difference scheme for a spring dashpot system in parallel, and that's described by the ODE given in the problem sheet. Some of these questions are analytical solutions, and I've given the written answers online on Ellie, but now I'm going to go through the bits that require MATLAB. The first part is 3b. It says write a script which solves the discrete equation from t equals 0 to 5 with u0 equals 0 and f equals eta equals k equals 1, and plot the results for different time steps. So we're going to write it in a script. So we're going to have example 3. And so we want to do this code for lots of different values of time step dt. So we're going to set up a vector which does 1.0, 0.5, 0.1 and 0.01. And we're going to write a for loop which goes for j equals 1 to the length dt. Basically, we're going to repeat whatever we do for each case, for each different value of dt. Right. We then got some common values for each run, so we have f equals 1, eta equals 1, and k equals 1. Right. And we are now going to, we want to solve this for over the time period, so the number of the time vector depends on my time step. So for each time it's going to be from 0 in intervals of dt of j. So for this case, for this specific value of dt in the loop, up to 5. And then I'm going to initialize my solution vector, which is going to be initially zeros, a row vector of zeros of the same length as t. Now I want to find the corresponding u for each t, so I'm going to set up a for loop. So I know what the first value of u is. It's 0 from my boundary conditions. So I want to run this vector from I equals 2 up to the length of t, and then I can write the difference equation, discrete equation in, which is what I asked you described in 3a. So that's ui equals ui minus 1 plus dt of j over eta times by f minus ui minus 1. There's k in there as well, so k times k. Okay, and I want to plot these results. So here we go. What happened there? Figure 1, plot t and against u. And we want to overlay the plots, so we're going to put a hold on command. So we're going to save this example and run it, so hopefully we'll get the solution for different time steps, which we get here. We can see that the solution converges to a nice smooth path, which is hopefully the same as the analytical solution, which I asked you to derive in the following question. So 3c is find the analytical solution and plot it. So how you derive the analytical solution using the integration factor is online. So here I will just plot it. So I'm going to write the question if j equals the length of dt. So if we are the last time step, we will plot u of e equals And from my notes, you will see that the solution is f over k times 1 minus x minus k over eta times t. So then we can write figure 1 t, the exact solution UE, we do that with red stars, and the if. So let's save that, so it's saved. We can rerun the script. You can see that, yeah, I did get the analytical solution right. It agrees, red dots, it swamped some of the finer time step calculations. So the final, more challenging last part of this is to calculate how the error scales. And we need to calculate what we call the L2 norm of the error. So this the difference between the error squared integrated over the full time. To do this, we are going to introduce a fine mesh. To integrate over. So it's going to be bin space. Oh, not bin space. So 0 to very fine time step 0.01 up to 5. And then we're actually going to use the interp command. So we're going to calculate a U-fine, which is going to do interp 1, which takes values t and u and finds intermediate values at tf. It's then going to calculate the error. So I want to find the error for each of the dt. So we're going to do zeros, 1, length dt. So E of j equals traps. So traps finds the numerical integration using trapezoidal rule, and that's why we use a fine mesh, so that the trapezoidal rule is very accurate. And then we want to do it over TF, which is from 0 to 5, and we want to calculate U fine minus this U exact squared, which we haven't defined yet. And we want to find the square root of this. And we're actually going to nick this from here. So this is the U exact fine solution. And then what I want you to do is work out the scaling between this error, E and dt. So the way you can do that is actually by not figure 1, we'll do it on a different plot. Axis equal, because we're going to have to measure the gradient of this line. And what we want to do is we want to plot log dt against, so we want, log E, log of the error on the y-axis, so log dt now if we run this script, we should get what we had before. So this is exactly what we had before without the plot of the exact solution. We can then ask for the values of E. Listens to me. E. So these are the errors for the time steps, so we see it decreasing over time. And then finally we can look at not figure 1 but figure 2. is a plot of log dt against log epsilon. So the gradient of this line is the alpha I asked you to calculate in the question, which tells you how the error scales with dt, and that finishes the final question I asked. Okay, yeah, the final thing that might be useful is I think the command help. So help is very useful because it enables you to look up how different commands are used. So this fits a polynomial of order n to 2 points. So what we will be interested in is a polyfit of log dt against log e. We want an order 1. And so what we actually see, so this is the constant and this is the gradient, and so we see that alpha is approximately minus 1.22. That's it.